Español. Okay, good afternoon. Now that we have had lunch and everybody is tired, I can start talking about why acceleration and short waves. I hope my brain still functions at least a little bit during the talk. So the idea is to discuss how the turbulence in the upstream medium is affected by shock wave that goes through it, and what kind of effects the transmission of the turbulence, here modeled as plasma waves, has on the acceleration properties of the shock. How this transmission process affects the acceleration by shocks. So we just have to get this good. So here's the outline of my talk. Let's first have a short introduction to the necessary terms in the cosmic ray transport equation that you need to understand acceleration of shock waves, and discuss a little bit the traditional traditional way of describing diffuse shock acceleration. And then I'm going to present the very simple-minded model of magnetic field fluctuations that I have used in this study. There is one important factor, which is the normalized cross-helicity of the waves, meaning that some sort of weighted average on the propagation direction of the waves relative to the ambient magnetic field. And the effect this property has on the actual scattering center compression ratio at shock waves. We are going to look in detail at the transmission of Alfvén waves and how that affects particle acceleration and parallel shocks, simply because that's doable analytically. And look at some features that are important for the Alfvén wave transmission, namely inclusion of the pressure of the Alfvén waves to the properties of the shock wave. I'm going to discuss a little bit about relativistic shocks also, and then point out some inevitable effects concerning downstream stochastic acceleration. Then have some discussion of the results and some outputs. Basically, what I'm describing here is described in these 5 papers, which 3 of them have already been published a while ago. These 2 studies are basically fresh and still not even reviewed. But let's go to the cosmic ray transport equation and transport coefficients first. I'm going to limit myself to 1D systems. So the shock wave is more or less one-dimensional. You have the upstream side, the downstream side, and the quantity can change, for example, the flow speed from a super alpinic super fast magnetosonic speed on the upstream side to sub magnetosonic one on the downstream side. And basically, the transport equation of cosmic rays is here, which you need to worry about. It contains convention as cosmic ray bulk speed, which is basically given by this kind of derivative here. You notice that if this A coefficient here is energy independent, then this is simply W equals A. And And the A coefficient here contains the plasma bulk speed as well as the term here that is related to the phase speed of the waves that are actually scattering the particles. We have the diffusion term here given by the standard diffusion coefficient parallel to the magnetic field is given by the standard formula here. d mu mu, d mu p, and dpp are actually the Fokker-Planck coefficients which are calculated from linearized particle orbits. Here mu is the cosmic ray pitch angle cosine, the angle the velocity vector makes with the magnetic field. Always have the magnetic field, the velocity vector of the cosmic ray. Here you have theta, which is part of the cosine of so these are the more or less the microscopic Fokker-Planck coefficients, and they are related to the macroscopic ones through these integrals over the pitch angle cosine here. And these coefficients here, d mu mu, d mu p, and dpp, they employ the fluctuating electromagnetic fields by containing, in the quasi-linear approach, they will contain the correlation tensor components of the magnetic field, of the fluctuations of the magnetic field and of the electric field fluctuations. Typically, cosmic ray acceleration models consider a case where d mu p is actually doesn't either it's neglected or then it's taken as a symmetric function with respect to mu, which means that it drops out from all of these intervals where it's supposed to appear, not from here, but from here. So in that case, if it's symmetric, antisymmetric, sorry, so order function of mu, then it vanishes from here and you will simply have v in this case. And typically, if you think about cosmic ray transport models, the only speed that is taken into account is the bulk speed of the plasma. But actually this, including the possibility for the scattering centers to flow at a speed which is different from the bulk plasma speed, is very vital for acceleration models if you consider shock waves with finite mass numbers. Let's start from the traditional picture of diffusion shock acceleration then. If we neglect all fluctuating electric fields in the local plasma frame, that's one way of doing it, saying that everything is frozen in to the bulk plasma flow. So in this case, the microscopic coefficients d mu p and dpp vanish. It means that the cosmic ray in velocity space, if you have the bulk speed here, for example, so this is parallel, perpendicular and parallel velocity relative to the magnetic field direction. Then you conserve the particle energy in the frame centered to the bulk speed of the plasma here. This is the main idea in Fermi acceleration models. So you have this kind of frame where your particle conserves its velocity, and then you have another frame on the other side of the shock wave, and having the particle cross and recross the shock many times gives the particle a possibility to actually gain energy in this by traveling on semicircles that are centered in this V1 and V2 here. So this is how the particle in Fermi acceleration gains its energy. But let's look at the macroscopic derivation of the spectrum. There you start with the cosmic ray transport equation I just showed, but because these vanish here, you only have convection by plasma speed and you don't have any stochastic acceleration included in this. I have added here also the typical description so that you inject some low energy particles at the shock wave to the acceleration process and then solve what kind of distribution function you get in the steady state. So you forget about the time derivative here. So if you do it, you look at the solution at the rest frame of the shock when you can place your shock at x equals 0. You have V1 here at negative values of x and V2 at positive values of x, and this now is given by V1 over the compression ratio of the shock wave here. And you require the continuity of the distribution function at x equals 0, and that the distribution function vanishes at x equals minus infinity far upstream, and then that it's limited far downstream, and the solution you get is over here. This is the standard picture. So you have the cosmic ray intensity that is basically, again, if your cosmic ray intensity as a function of position is here, this is upstream, and this is downstream. You have an exponentially increasing cosmic ray density here, and then a constant value downstream. And the spectrum of the cosmic rays, which I now give as a distribution function here, is a power law, and the power law spectral index is fully determined by the compression ratio of the shock.
It's just the regular compression, nothing else. No acceleration, just compression of the shock.
Well, actually, it's not adiabatic compression. In this case, you would not get the power law from for example, so if you have adiabatic compression, you will preserve your spectral index from the upstream to the downstream. So this is completely different. It's not adiabatic. It's the essential part of this derivation is that the diffusion length of the particles has to be much, much longer than the thickness of the shock. If that's not the case, you don't get any acceleration. It simply compress your cosmic ray gas. So you get
this condition appears here.
In a way that I treat this as a discontinuity. But in real life, the electromagnetic fluctuations are not purely magnetic in plasma frame. So you have electric fields, which means that the particle can change its energy also during the scattering process here. So it's not that simple. And especially, let's think about Alfvén waves, for example. They are static in the frame that co-moves with the waves. So if you have unidirectional Alfvén waves, they flow and in this direction. Then if you transform to the frame of the waves, then the magnetic field is static. You don't have any electric field. So then you could simply say that this is plus or minus VA here. This speed, where you do the ping pong play here. So basically, you could have a good guess that your wave speed is more or less between V minus VA and V plus VA, something like that. So the basic theory where you neglect all the fluctuating electric fields, that's okay if your Mach number is very large. For example, in supernova remnants going to the interstellar medium, at least during the first 100,000 years or so, that's probably just okay. But for example, in solar corona, in the acceleration of solar cosmic rays, this is never a good approximation, because there your Mach numbers are of the order of few. So the basic thing is that the turbulent electric fields are also crucial for diffusive shock acceleration, if you want to do it for low magnitude shocks. Now, let's model a little bit what kind of form of the fluctuations we could use in the theory, acceleration theory here. So let's think that these fluctuations are superpositions of incompressible MHD waves. So we have a turbulence, and we can somehow say that, okay, this is the weak turbulence approach, that you say that you have your normal modes of the plasma, which have to more or less your plasma wave modes have to more or less describe all the fluctuations. And here you would have break up your magnetic field into different wave vector components, and same for the electric field, and then you would have the sinusoidal form for these, and you would use Faraday's law to connect the electric field with the magnetic field, and then sum this Burton relation to give omega as a function of k for each component here. In this kind of way, you can actually calculate what the Fokker-Planck coefficients for the cosmic ray transport are. And what you get is that your pitch angle diffusion coefficient depends on the intensity of the magnetic waves at the resonant wave number, which is given, basically it's an inverse Larmor radius, more or less. And here you have geometric factor, more or less, sine squared of the pitch angle, and here is the cosmic ray Larmor frequency or gyro frequency, that's the relativistic one. And these other Fokker-Planck coefficients can be simply given by the aid of the And now if you take a certain form, so power law spectrum for the fluctuations here, where Q could be, for example, 5/3 for Kolmogorov spectrum or something like that, and sum the effects of parallel propagating and anti-parallel propagating waves, then you get your diffusion coefficients and your other transport coefficients, like this.
Again, what is V small squared?
Oh, sorry. This is cosmic ray speed. Cosmic ray speed, so it's basically speed of light. But this is also for non-relativistic particles, so that's why you don't see C here. This is valid for both relativistic and non-relativistic particles. So what enters into the parallel diffusion coefficient is basically the inverse of the normalized wave power here. So your wave intensity as normalized to the ambient magnetic field is here, and summing up the total contributions gets you here. This T here, that was the momentum space diffusion coefficient. That contains the intensity of waves in the numerator. So here, if you have a low intensity, the mean free path, the diffusion coefficient is large. But if you have a low intensity, then your momentum space diffusion coefficient is small. That's natural. And then what you get entering the formulas also is now the normalized cross helicity of the waves. So this basically measures the average propagation direction of your alpha waves, more or less, relative to the plasma. And this enters, so if all, first of all, it enters this A coefficient here. So now we are sitting in a plasma frame with this cross helicity is different from 0. So if there's more alpha waves going in one direction than the other, then of course the cosmic rays follow the average wave speed more or less. They are convected by the waves. But here it makes another kind of contribution, because if all your waves are going in one direction, which means that your HC is either plus or minus 1, put 1 to 0, then of these two coefficients here, you see that you get plus or minus 1, then you don't get any momentum diffusion. And this is also natural, because it was just, we put all the wave power again in a single field, so you don't get stochastic acceleration. Stochastic acceleration comes about if your particle is able to scatter from more than one wave field, so that you can do this kind of So if I now take this to be V plus VA, and this to be V minus VA, then I would have stochastic acceleration, because now the particles would be scattered by these waves and these waves, and again gain energy in the velocity space.
Again, it's for subalternic motions, right? So in the advection speed, this H dominates the bulk velocity of plasma.
This is simply when you calculate everything sitting in the plasma frame, so you don't allow any motion. If you go to the fixed frame, more or less, where you allow the plasma motion, then actually the wave speed is simply this plus the plasma speed. And the cross helicity is again given by the same formula here, and your D, this is simply repetition. Now, in the very vital ingredient of the original paper by Bell on diffusion shock acceleration was the fact that he didn't invent any scattering mechanism, but he showed that the two-stream instability by the cosmic rays in the upstream region is able to generate Alfvén waves at the resonant frequencies. So he relied on turbulence that was completely self-generated by the particles that are accelerated during the process. So in this case, it's actually the waves that are streaming, how should I put it, here. So the plasma is going in this direction. Here in the upstream region, actually your cosmic rays are more or less isotropic in the frame of the shock. So in the frame of the plasma, the streaming of cosmic rays is always in this direction, against the flow. And by simple considerations, you can figure out that the unstable wave component is the one going in the same direction as the particle stream, more or less. That's the one that is excited. So here in the upstream medium, you would get your V as W as V minus V. So here the scattering and the speed is something like this. This is old news. This is what was already written in Bell's paper in the original one. Another consequence is that you only have these unstable waves, so you don't have any stochastic acceleration in the upstream region. So basically you can, if you now neglect stochastic acceleration from the downstream region also, you can write down the spectrum again in the same form as before, but now remembering that you have actually a scattering center compression ratio that is determining the spectral index of the cosmic rays. And by this I mean that you have to use the W on both sides. So this is W1 here, and you would have a W2 here, which would be somewhere between V2 minus VA2 and V2 plus. But we don't know where, because we don't know yet what is the downstream cross helicity of the waves. It's not clear. But actually, making your life much more simpler again than relying on MHD shock waves, so describing shocks as discontinuities. You can use the jump conditions and calculate what HC2 should be if all the fluctuating fields are still superpositions of Alfvén, also in the downstream. And this is what we have done there. It gets very messy if you allow oblique magnetic fields. So if here your magnetic field can have psi minus actually here, so if your magnetic field, regular magnetic field can be anything else but normal to the shock front, then this calculation is a bit more messy, because your Alfvén waves, which are fluctuating strictly perpendicular to the mean field, are actually exciting some fluctuations parallel to the field. That means magnetosonic waves to the downstream region. It's not analytically doable, and you have to resort to numerical methods. You can do that, but for the demonstration purpose, I'm sticking to the parallel case here. So we use MHD jump conditions for the basically the transverse electric transverse electric field and transverse momentum, and calculate the downstream tangential components of the flow speed and magnetic field from the upstream ones. This is simple. It's been done since 1969 for Earth's explosion, for example. Here, again, the compression ratio R is given by actually the normal components of the shock. So now we are talking about parallel shocks, which means that we don't have any transverse components. So this sounds a bit silly, but then the transverse component comes about as a form of waves. So the only transverse components we are allowing here is the component by the waves themselves in the upstream region. And so we may have waves that propagate against the flow, like these ones, and then waves that propagate in the same direction as the flow, which I use plus sign for, and they would go like this. And then using the Walian condition for the velocity, the relation between the magnetic field and velocity in an atom, and quickly write down this one, and then figure out what is the portion of downstream waves going in both directions from given upstream conditions. So you can solve for downstream amplitudes and get some transmission coefficients, which I use T and R for. So it's basically the downstream amplitude divided by upstream amplitude. And now here, actually what happens is that even when you have a unidirectional wave field in the upstream region, you always excite waves going in both directions in downstream. You cannot have unidirectional wave field in the downstream anymore. It's simply not possible with these equations to have it. Which means that in my case, I use T if the wave retains its propagation direction. So T minus, for example, would be the amplitude of the backward propagating downward waves divided by the amplitude of the backward propagating upstream waves. And R minus would be downstream amplitude of the forward propagating wave divided by upstream amplitude of backward propagating wave. So that's a notation. And what you get here is something that depends on Mach number and compression ratio. And of course, in the shock wave, these two are coupled, so you can basically calculate what your transmission coefficients and what kind of turbulence you have downstream. But the previous calculation was done basically at constant wave frequency. So we were following one wave, and because the wave has to conserve its frequency at this boundary here, we were doing a calculation of constant wave frequency measured in the shock frame, but cosmic rays feel the wave at constant wave number. So the cosmic ray of certain energy feels a certain wave number here, and it's the same wave number here downstream, whereas for the wave itself, the wave is simply compressed when you put it downstream, so the K vector is actually increasing when you go to the downstream side of the shock. So you have to do it for a certain spectrum of waves, where I again use this power law type spectrum of waves, and then calculate now at more or less the cross helicity of the downstream waves at constant wave number, and plot it here for a parallel shock wave. So in test wave approach, we can simply take the compression ratio of a parallel shock wave here and substitute it for all R's, or vice versa, substitute it M's for all R's, as is done in these figures here. And you get downstream cross helicities that are very close to -1 for compression ratios that are small, but for a larger value of plasma beta here, I have a plasma beta value of 1.2 here, I will get something that is between -1 and 1. Now I can calculate the scattering center compression ratio for these shocks. The first thing that I notice is that if I have plasma beta of the order of unity, the scattering center compression ratio as a function of gas compression ratio is basically flat. So, in this sense, all shocks are as good as any other shocks. And this is a little bit surprising result. But even more surprising result is when I go to small values of plasma beta. Here, actually, the scattering center compression ratio explodes. This is because now this V2 here gets very close to the A. So for these waves that propagate against the flow, they become standing in the shock frame. So there you pump up energy into this field and they don't fly away. So they get here and their amplitude is increased. That's why you get sort of a standing Alfvén wavefront, not standing, but very slowly propagating Alfvén wavefront behind the shock calculation. And this Alfvén wavefront will have large intensity, and that will be able to scatter the particles very efficiently. So the scattering and the compression ratio becomes very large. Formally, it reaches infinity at this limit when you go to Mach number that is given by this expression here. So if beta is less than unity, this will be big. But this is not, of course, not the case, because if you consider this situation a little bit more carefully, you realize that what you missed from your calculation of the compression ratio of the shock was the pressure that is exerted by the waves themselves to the shock wave. So you have to take that into account. When you do, you see that your compression ratios never actually reach this limiting curve here, which is the singularity here. So this is Alfvénic Mach number, this is gas compression ratio, and this is now the R equals n squared curve, this dashed curve here. And if your B parameter, which is the wave amplitude normalized to the ambient field in the upstream region, if it's non-zero, then your shock will always be able to escape this singularity here. So you get a scattering center compression ratio and downstream wave intensity which are large for n less than about 2, but not infinite. So that's possible. So now repeating the same figures, the downstream cross helicity and the scattering center compression ratio as a function of gas compression ratio of the shock for the self-consistent R, where wave pressure is included, you will then get very much downstream waves propagating in backward direction and basically at all compression ratios of the shock. So this now here, the solid curves are for upstream cross helicity of -1, which was the case of unstable waves. So this is basically the physical case you should consider in non-relativistic shocks. What does it mean for spectral index? Now I have plotted the cosmic ray energy spectrum, which is given by the distribution function multiplied by P squared here, and that is of course proportional to P to 2 minus sigma power here. So this spectral index gamma, which results from this, is actually the scattering center compression ratio plus root over scattering center compression ratio -1, which means that the spectral index will be very, very flat from this theory for shock waves which propagate into low beta plasma. Now I have given it as a function of gas compression ratio of the shock as well as spectral index of the traditional theory where you don't include wave propagation. Again, for plasma beta of the unit order, all shocks seem to produce spectral indices that are between 2 and 3, more or less. Quite nice result. But for low beta plasmas, you have the possibility, such as in solar corona, where you have weak shocks. We have shock-accelerated particle events. So this is one way of understanding. We have low beta plasma where we have parallel shocks, and these are able to accelerate fast spectra, although they are relatively weak. So low Mach number parallel shock waves propagating in low beta plasma produce flat spectra. Now I have extended, we have also calculated this for relativistic shocks, but here one has to understand that it's of course the requirement for parallel geometry is even more restrictive in this case, because if you have a gamma factor for the shock, for example, then the parameter range where the upstream magnetic field in the shock frame is parallel is very limited. So immediately, if you have some tangential component of the upstream field in the plasma frame, when you boost to the shock frame, it will be more or less tangential all the way in the upstream frame. So these are a bit more restrictive, but maybe you can have, for example, models of jets where you have some spine magnetic field and then some maybe other having a toroidal component in lines that are a little bit further away, and then if you have a shock wave propagating fast in this kind of jet, you may have regions where you develop parallel geometries. And of course, because you are talking about relativistic jets, you want to have very large alpha speeds in order to have any effects, low Mach numbers, then you have to retreat to pair plasma composition, because otherwise your mass density will be high and your magnetic field has to be enormous to get alpha speeds that are relativistic. So these conditions could be applied in some relativistic jet models, perhaps. So again, an evolutionary. I've only done this in a test wave approach, not calculating the gas compression ratio so consistently, and assumed now that there is little chance of particles to produce actually this kind of precursor in a relativistic shock that's reasonable. So I've taken this H in the upstream region probability to be 0, resulting from some external processes. So what you get, downstream cross-helicity again for low Mach number shocks very close to -1. So now I have plotted the scattering center compression ratio divided by the gas compression ratio of the shock, the function of Mach number over a critical one, which is more or less the singularity here, and you get very large values of the scattering center compression ratio also in these shocks, which means that your relativistic shock cosmic ray spectrum is not the 2.2 that people always quote. So as you know, the relativistic simulations, all relativistic shocks should produce always a spectral index which is very close to 2.2, but it can be anything between 2.2 and 1 according to this calculation, when you include wave propagation effects. And this, by the way, has to be actually simulated because you don't use the diffusion approximation for the transport theory anymore. So this is simulated using a Monte Carlo wave. And then you have diffusion shock acceleration prediction overplotted with the simulations. You see that when you go to higher values of the proper speed of the shock wave, your theory doesn't produce very good results, as it of course shouldn't. Then, about the possibility of stochastic acceleration at the shock. Downstream plasma always contains waves propagating in both directions, so you should have stochastic acceleration. One way of estimate, and if it's important, is to compare the time scale involved in the first order process, which is basically given by this expression here. You have the mean-free path over or the diffusion coefficient over the squared wave speed in the upstream region, and then this one for the downstream time scale for, so this is momentum diffusion coefficient. And actually this ratio of time scales is independent of momentum. Plug in those values. And for the physical case where you have for HC1 minus 1, you get that the ratio of the second order process is much, or the time scale of the second order process is much larger than of the first order process. So at least at the shock wave, your spectrum is well modeled. But what about far downstream? Because actually now you launch your cosmic rays to this direction along with the waves, so they will be able to damp the waves and accelerate stochastically. I should just show you what that affects. Basically, the spectral shape is no longer a power law, but you produce at low energies some sort of bumps in a high energy state. This, if you have a reacceleration. What this is maybe not too surprising, but if you then allow additionally a continuous injection of particles from the downstream plasma population to the stochastic acceleration process, then you again have Fermi 1, then you again have actually power loss. So this is now the log of electron energy, location, and then contours of the energy spectrum of the electrons here. One is, we have used a model where our scattering frequency goes down at certain momentum, at certain electron energies, which means that we are actually able to get the particles back to the shock and produce another bump in the spectrum. That's the detail of it. Yeah, okay, I will just come to the end. So let's skip this one. If you do it for oblique shock, it gets more messy, and probably there are important factors which we have neglected. That's compression, for example, compressional turbulence, because the wave speed is then fast momentosonic speed, which is very different in the downstream region from the outlet speed. Electron transport at mildly suprathermal energies is not covered by MHD turbulence, so we should use whispers instead. Effects of turbulent cascading will be very important. They will produce probably quasi-isotropic path mode component plus the quasi-two-dimensional alpha and level slow mode component. And it removes power from these waves that are able to scatter the particles. So we need plasma simulations actually to verify the wave transmission calculations we have done. And then one can actually ask the question, can strong turbulence in the downstream region be represented as a superposition of waves or not? Okay, thanks.
Maybe you can illuminate us on the apparent discrepancy between the summations that were yesterday presented by Hedegaard and Fredriksson.
Yeah, you mean the absence of Fermi in the
yes.
First of all, these were relativistic shocks.
Yeah.
With, I think, extremely narrow downstream region. So one may question if the particles ever have a chance to get back to the shock again. I think you talked about the thermalization of protons considerations. You said that they are only mildly thermalized, so the level of thermalization was very low. Maybe that means that your downstream region should be much, much larger to actually get the particles going back to us. phase, and then you would get the chance for these particles to enter the permafrost. I don't know, that's my feeling.
Yeah.
And then one important point which I realized, actually this kind of calculation where you approximate the shock as a disconnecting relief, it's not good for relativistic shocks, except for bare plasmas where you don't have the inertia of the ions. They show quite convincingly that the shock is very extended actually, compared to the long radius of the particles. So you actually need to use something that they are doing, maybe a little bit, or let's say a couple of orders of magnitude extension to the box size.
You can ask a computer.
Okay, maybe.
Yeah.
Why not? Just asking about the relevance of the second order thermal process for the bulk cosmic rays in the galaxy. Would you agree that the bulk energy that the cosmic rays gain is by first order thermal, or this is just a re-acceleration term?
Yeah, I would say that's the case. Basically, what I didn't tell you about this simulation was that it's a test wave approach. So the waves are there, even if they are damped all the time. So in these kind of simulations, when you do a test particle calculation, your energy reservoir in the waves is infinite. So you can get large effects from downstream stochastic acceleration, but you have to be careful because if you calculate the energy density, you jump into the particles, and that's away from the waves and decreases the acceleration. So I would probably agree with you that it's more like a minor effect.
But you wouldn't think that you could actually boost the maximum energy in the cosmic rays by this
Maybe you could.
re-acceleration?
Maybe you could, because as I told you, if you have downstream stochastic acceleration, you produce a downstream spectrum at the shock like this, for example. And then if your mean free path starts to increase at some energy, and you are able by downstream stochastic acceleration to shift the particles here, then they can go back towards the shock again and be sort of re-injected to the shock acceleration process. So it may produce funny and quite nice results. In the simulation, we pick up spectra that have more or less two components because of this re-acceleration.
So you can get beyond the need with the...
That's a matter of parameters. I would say, I'm not sure if I can really get beyond the need. I haven't tried.
Okay, let's go to the next slide.
I will talk about acceleration of cosmic rays in galactic wind, and these are the main topics of this talk. And so let's start with some observations. Well, maybe you know these pictures. There is a lot of examples now of observed galactic winds. Here, in the case of NGC 1482. The observations show that you find, for example, ionized hydrogen up to a distance above the galactic plane to about 1.5 kiloparsecs, and probably also further away, but this is very difficult then to observe. From spectroscopic data you get velocities of the order of about 250 kilometers, and if you...
But this is less than escape velocity, right? This is less than the escape velocity. So this window doesn't extend to infinity.
It's not clear. I mean, this is as far as you can do spectroscopy. You know, this does not mean that this cannot escape. It's just, the problem is that the intensity is getting so low up there that it's very hard to observe.
Because they're accelerated further.
Yeah. And you will see that usually you are getting much higher speeds if you go to much larger distances from the plane. And well, the kinetic energy you estimate from this is of the order of about 100 supernova explosions. So there is a lot of energy in these flows. And we can also go further away. For example, this is a very funny shaped line. You observe, for example, at a redshift of 5.1, and if you do the analysis of this line, of this Lyman alpha profile, you can decompose it and find three components. First, you see the recombination of the hot gas, which is assumed to be a starburst. Then you see this broad redshift part, from which is due to scattering of the backside of the flow, and then you see also blue shifted approaching wind, and therefore the interpretation of this line shape is that you find here a galactic wind of the order of around 300 kilometers per second. So this seems not to be an effect which is only, so to say, restricted to nowadays galaxies, so to say, but this should be a phenomenon which is occurring during different phases in a galactic life. And also famous example is NGC 253, where you find magnetic field and X-ray emission, and there are a lot of now observed starburst galaxies edge on, where you really can decompose the halo from the disk part, and you find large-scale magnetic fields. And there was also a lot of discussion already on the structure of these fields. But this is only just to introduce that the idea is that it may be a number of phases that you have massive outflows from galaxies connecting the galactic halo to the disk. And the idea is that the magnetic field is transported outward. You see also high temperature gas above the galactic plane. All these are indications of having a galactic wind, and you find also gradients. Of course, you have the most activities going in the center, and there you find a gradient in temperature from the center going out into the halo. Now, what can you do, or what is a simple physical model? The basic idea is that you have, of course, supernova and collective effect of supernova, superbubble. So the supernova activity is going on in the galaxy, producing thermal pressure, producing cosmic rays, and also elephant waves. Due to the collective effect of these three pressure gradients, you can produce an outflow. And a simple picture is that you assume, as depicted here, flux loop geometry, so meaning that all variables depend on time and on distance from the galactic plane. And the disadvantage by this approach is that you have to specify this area of the flux loop as a function of the distance from the galactic plane. On the other hand, you can include various sources of time dependence. You will see that you can generate shock waves propagating through such a flux tube. You have particle acceleration, you have heating due to the dissipation of waves, and you can include also diffusion as well as radiative losses. And I will present here numerical solutions on a one-dimensional adaptive grid, which is necessary to resolve in all these flow features. So all the variables are depending only on time and on this parameter set. Now, what do we want to explain? We want basically to explain, or at least an idea, how to be able to generate the energies which are above the so-called knee. It is not directly observed, but it's mostly believed that up to this energy of about 10 to the 15 electron volts, that these particles can be accelerated in supernova remnants by this first order Fermi process. But this first order Fermi process is very hard to really see from the observational point of view. I would like to stress again that if you have particle acceleration in a supernova remnant, you will not see it by totally smeared out shock waves or something like that. It's only a minor modification of the shock wave, and all fluctuations in the density, for example, in the external medium or something like that, would be much more severe on the shock structure than these modifications into cosmic rays. Nevertheless, as you will see, there is about maybe 15 or 10 to 15% of the total energy of a supernova remnant can be transferred into cosmic rays. But it does not mean that this is an easy or easy to see observational evidence for particle acceleration. Well, we have discussed that here a lot, that the cosmic ray energy density is comparable to all other components of the interstellar medium. I want to repeat this equipartition discussion again. I treat the cosmic rays as a relativistic gas with a adiabatic index of 4/3. And we have already seen or discussed it a lot that if you go to this high energy regime, then the gyration radio of the cosmic rays can become comparable to the disk size of the galaxy. So the cosmic rays, if you want to accelerate them, you need large scale and long-lasting shock waves, otherwise this mechanism of particle acceleration does not work. So, as I repeated, or as we have discussed today, I would like to say that in this model the cosmic rays are reflected at the velocity plus the alpha velocity because the alpha waves they go always outward. So it's comparing to the previous talk, velocity of 1, which is used here. There is also the problem that when we observe the cosmic ray particle spectrum is different from the source spectrum due to the energy-dependent transport, and the problem again, it's only now marginal observational evidence that cosmic rays are really accelerated. And I will use 3 kind of energy equations, one for the thermal plasma, one for the cosmic rays, and the third one for the magnetic waves, which then couple the cosmic rays through the thermal plasma. Now, let's make a short excursion to supernova explosions, because we have here a lot of discussion on the supernova and how the supernova are really depositing their energy into the interstellar medium. So you have the source of energy, which is then shared by the kinetic, thermal, as well as cosmic ray energy, and we will see how this is then done. And it's also important, if you really want to see what is the final outcome of cosmic rays on a supernova remnant, to extend the calculations into the cooling phase. It's no use to stop in the zero phase, because we will see that the main acceleration of cosmic rays really starts at the end of the zero phase, when the remnant enters the cooling phase. And as, for example, a galactic wind goes on, it will lose mass into the intergalactic medium, and for example, if this is into a starburst region, then the mean density decreases and will maybe also the star formation comes then to an end, and by that it's also the possibility that the galactic wind couples back to the starburst region on the other hand, and that the evolution of the interstellar medium in this starburst region is really largely dominated by the evolution of the galactic wind, and also the cosmic rays and particle diffusion may play an important role how such a outflow develops in time.
Sorry about that mean density decrease. That wind is very hot. The density is very low. Even though the cosmic flux, the mass flux should be quite small.
No, but you can have, for example, a lot of energy transfer from the wind, and you can also accelerate or take with the wind, for example, molecular clouds. Usually, if you look into the observations, it seems to be that there is a mixture of hot and cold gas in this wind. So therefore, you can decrease the density, which is then, or some kind of, the density also of the cold gas, which is then introduced or making or producing stars. What you see here, for example, is as a function of density and of age, going here from 1,000 years to 100,000 years. And here you see the amount of cosmic ray energy which is converted, or the amount of supernova energy which is converted into cosmic rays. So you have here different effects. In particular, if you go, for example, to the higher densities, then the cosmic ray efficiency of accelerating particles goes down because the cooling phase starts too early. You need some time to accelerate particles, and you need a fast-running shock wave to do that. But if then cooling starts and sets in too early, then the acceleration of cosmic rays goes down. This bump here, this is due to the acceleration of particles in the reverse shock, which is more important if you go to low densities. If you go to high densities, then the main acceleration is done in the forward shock. But you see that typically around 15% or maybe 30% in the optimum case of the energy can be transferred into cosmic rays. Of course, this depends also on the magnetic field you assume in the interstellar medium, because this determines, for example, the diffusion coefficient.
May I ask, what is the reason for the growth of the efficiency of cosmic ray acceleration in time? Why is the late stages of the supernova remnant are more better for the acceleration?
The reason is that due to the diffusion, for example, due to the diffusion coefficient, you need some time. Otherwise, it's not a process which goes instantaneously. Of course, it's local, but it has to grow, and then, so to say, the total energy is then also growing with time and with volume. Basically, you have at the first or the initial stages, you have acceleration of particles, but these are confined to such a small volume that the total amount of energy in the cosmic rays is not, it's negligible compared to the total energy available in the supernova. So it takes some time. Yeah. It's also an important point that due to the fact that this is a highly relativistic gas, also the adiabatic losses are much less than in the thermal gas, which is gamma 5/3. And you have, in addition to this advection, or some people call it also convection, this convected or advected transport is again only part. The other part is that due to diffusion, you have transport of particles, and in particular it's also important to consider the diffusion of the particles from the shock wave again back into the interior of the supernova, which is a very important problem, because a lot of this computation of supernova remnants in particular, the computations give you this very high efficiency. They do not include this loss of particles due to diffusion into the interior. And therefore the energetic particles, they stay too long near the shock waves and get there re-accelerated and re-accelerated. So the diffusive losses into the supernova remnant filling out the energy density inside of the shock are very important. And then is of course this was on supernova remnants, but if you now think of galactic winds, there is of course also the possibility that the flux or the energy density of the cosmic rays, which can be, for example, accelerated in shock waves in the outflowing material, can also interact with the galactic plane again. And as I said, due to the fact that you have an additional energy equation, you have a coupling of the waves with the thermal plasma. Now let's look at such a typical supernova remnant evolution, which you see here as a function of time, logarithmic. The energy is 10 to the 51 ergs, and this is the particle density of one particle per cubic centimeter. And what you see here are the different energy contributions, and if you then go beyond 10 to the 4 here, beyond 10,000 years, you see that the radiative cooling losses become very dominant. What you see here is the thermal energy. So here you have almost everything is kinetic energy. The kinetic energy is this curve. You have the so-called free expansion. Then you have the transition from the free expansion to the Sedov phase, meaning that the kinetic energy goes down, the thermal energy goes up, and then here you have the reverse shock, which is a minor contribution, but then you have the Sedov phase, and if you don't include cooling, then the thermal energy stays at that level. But what happens is now that you have then, in this case, equilibrium cooling, radiative cooling, so the total amount of the energy contained within the shock front really goes down, and if you look up to the late phases, 10 to the 6 years, you see that the whole energy contained in this bubble is about 30%, and 15% is cosmic rays, about 7% is thermal energy, and then again the other 7% are kinetic energy. So if you see on this picture, most of the energy still contained in this supernova remnant after 1 million years is cosmic rays. It's 15% out of 30%. And this quantity depends also on the external density. Now these lines, for example, here correspond to the sweep-up time, where you have a transition from the free expansion to the Sedov phase.
So the sweep-up time. What is sweep-up time?
The sweep-up time is when the ejected material becomes equal to the material which is blown away by the...
So that's the end of the Sedov phase.
Yeah, the end of the Sedov phase, yeah. And just to... These are full numerical simulations, and these are the analytical estimates you can make by cooling time and so. So what you see is that the particles, the acceleration of particles, they start really at the Sedov phase, and if you have very high cosmic rays, you can also you generate waves, waves dissipate and heat the thermal plasma. Therefore, you can have here an increase of thermal energy and a decrease of cosmic ray energy again in the late phases. And as you've seen, most of the energy is radiated away. And if you don't like to have the thing on a time scale, here is a linear scale on the radius. You see how the shock radius is a function of time, and you see that you need to wait a few parsecs to see how the cosmic rays come up and then stay almost constant during the Sedov phase. Here again you have this cooling effect due to the most of the energy which is radiated away, and this here is the curve corresponding to the thermal energy. And of course, this thing here depends strongly on the density, as you have seen before. So when you do simulations like you should not keep this parameter epsilon constant, so epsilon depends strongly on the density. I would suggest. Well, now, what is the physical input of this? Now, let's come to the particle acceleration. As I told you, we solve three energy equations. The whole system is called cosmic ray hydrodynamics. So we don't solve for the particle spectrum. We have a gravitational potential. We have outflow at the outer boundary conditions, and we put the inner boundary condition at reference level, depending on what kind of galaxy we want to simulate. For example, 100 parsec in the case of a starburst galaxy, or in the case of a Milky Way, the reference level where the flux tube stars was located at 1 kiloparsec above the galactic plane. Now, what you can first of course do is look if this numerical simulations corresponds or give the same result as these stationary winds from ordinary differential equations we have calculated, for example, by Peter Breitschwert. And the new thing is here that, for example, you specify the flux, which is the initial condition, and this consists of two parts. This is the flux which is attracted away by the velocity plus the unfeigned velocity, and in addition, of course, you have here this term which gives the loss of cosmic rays due to the diffusion, or kappa is the diffusion coefficient. And in the stationary solution, the velocity is determined through, or the mass loss is determined through the parameters at the critical point. And for a flux tube geometry, I adopted such a description, meaning that if you are in the vicinity of the disk, you have more or less a cylindrical geometry, but then if you go to large values or large distances, the flux tube opens and you have more or less a spherical divergence flow. Now, some solutions for the Milky Way.
But the scale there must be kiloparsecs, right? Because
yes.
cylindrical geometry is preserved.
The scale out, the normalization was, I think, 50 kiloparsecs.
Well, it's usually of the order of the radius of the galaxy, more or less.
Yeah. It was. Now, what you see here, I mean, the simulations go further out, but then almost nothing more interesting is happening. Here is up to a distance of 200 kiloparsec. You see the change of the variation of the density, the cosmic ray pressure, the gas pressure, and here the ratio of the cosmic ray pressure to the gas pressure. And what you see here is that as you go further out, the importance of the gas pressure decreases. In particular, you see here different solutions with different kind of diffusion coefficients. What was happening, that is, if you remember this condition of the flux is kept constant, and you have two parts. You have the advected flux and you have the diffusive flux, and this is, if you keep the flux constant and you increase the diffusion coefficient, what happens is that the winds become more faster, because the cosmic rays can more easily go away from the galaxy, but on the other hand, the density goes down. So, because the mass transported away by these winds is the velocity times the density, and with the cosmic rays you have two possibilities. You have the velocity and the diffusive flux. So if the total flux is kept constant and you increase the diffusive flux, then the velocity goes down and therefore the density goes down. Therefore, if you increase the cosmic ray diffusion, you get faster but also thinner winds. So in the case of the galaxy, the cosmic rays play an important role in driving the galactic winds. Of course, if you look then, for example, in other galaxies, and we know that already from the work of Tito Breitschwert, that of course radiative cooling is very important here in the case of equilibrium cooling, which can really change the temperature structure in this outflow by large amounts. But I will concentrate then on the particle acceleration. You can see that the main particle acceleration in these winds is really going on here near the galactic plane. And near the galactic plane, cooling is not an important quantity. Now, usually these were, so to say, time-dependent solutions. Now, if we look into time-dependent winds, usually it's the case that the galaxy is a dynamic system, so there are supernova remnants or repeated supernova explosions going on, and therefore you can have waves traveling, shock waves, for example, traveling into this galactic wind. On the other hand, of course, you will have particle acceleration and diffusion, which can smooth out some of these variations due to the fact that the particles are accelerated in these flows, and if they are accelerated, they take out kinetic energy of the flow and therefore smoothing out some of the structures. And as I said before, in the case of galactic winds from starbursts, they have so much energy that usually the thermal pressure dominates the wind, but if you go to some normal galaxies, for example, as like our Milky Way, then the effects of cosmic rays are much more important in driving or determining the final amount of the outflow, and it must then be done by observations, and in particular it's difficult, but it should be done to see or to have detailed velocity measurements to disentangle these two effects between cosmic rays and thermal plasma. Now, as an example, for example, a model for the galaxy M82, where you have a change of the cosmic ray and thermal pressure, and what happens is that you see that such a pattern is moving outwards in the galactic wind. It's similar to what you find in the supernova, where you have a forward shock, a contact discontinuity in between, and then a reverse shock. And of course, the fastest shock is the forward shock, the reverse shock is in the frame of the contact discontinuity running backwards, but opposite to a supernova remnant, you have a constant input, a constant outflow, and therefore this shock, the reverse shock, is not running back into the galaxy, but it is advected outwards. And if you plot, for example, the shock location as a function of time, here in units of years, here radius of kiloparsecs, you can easily trace the different discontinuities. Here you have the forward shock, here in between the contact discontinuity between these two states, and here you have the reverse shock going outward. And if you look here, almost linear velocity, this is due to the fact that you have this more or less spherical divergence. You can understand that was some kind of similarity solutions. These are typically velocities of these disturbances going outwards. And now, what you can do is, you can take these models and calculate in these models how particles, for example, which are available from the cosmic rays in the disk, how they are then re-accelerated or accelerated on these traveling shock waves by a first order thermal mechanism. And this, of course, depends also on the diffusion coefficient. And what you can do here is, for example, just for the first step, try to solve this differential equation and look how much energy you can get, how large can the momentum get in this acceleration process. In the usual test particle picture, you have here an expression for the acceleration time, and from that, if you put that all together, you can calculate here a simple equation which tells you as a function of time how the particle energy, or here the momentum, goes up in time, and the long-term evolution is simply given by this analytical expression, so you can understand how you get this almost constant behavior. Of course, if you take into consideration only the forward shock, you get less energies, but if you take into the consideration these two shocks, forward and backward shocks, you can accelerate the particle to much higher energies. As I said before, now here as a function of radius of the shock front, you see, as I told you before, all the acceleration occurs near the galaxy. So it's no problem to get these high energy particles back from far away, because there were, for example, models where you generate these high energy particles at the galactic terminal shock, wherever this is, and then you have to propagate all these particles back again. If you have shock waves running through such galactic winds, you see that the main acceleration really goes near, or goes on near the galactic disk. So it's no problem for these high energy particles to travel a few kiloparsec or diffuse back a few kiloparsec. It's rather difficult if they are accelerated 300 or 400 kiloparsecs outwards, and then they have to go back, diffuse backwards again against this galactic outflow. As you see, of course, the final energy you get depends on the energy where you inject your particles. So it depends on the momentum. This is process as you've seen before. And what you expect is that due to repeated shock waves, you have several supernova explosions which are going on in such a superbubble, and there you can have several shock waves traveling through the same region, and every shock wave re-accelerates the particles. Then they have time to diffuse back, and then they get picked up by the next shock wave coming from the next supernova remnant, and then they can get accelerated. And the nice thing with this mechanism is that you have the same process. The supernova remnants, they accelerate your particles up to the knee, but the same supernova remnants, they can also propagate, or shock waves from them can also propagate into the galactic wind, and then they re-accelerate the particles above the knee. So there's no problem in matching these two kind of slopes, because it's the same physical mechanism who does the acceleration of the particle. Now, as you have seen, there are a lot of time-dependent effects, and they are important to determine the properties of the galactic wind. You've seen that from normal galaxies, the galactic winds are strongly influenced by cosmic rays. If you do galactic winds from starburst galaxies, then normally the thermal effects are dominating the outflows, therefore cosmic rays are less important. We have also seen that the shock waves generated by these repeated supernova explosions, they can re-accelerate the particles, and this re-acceleration process is really going on near the galactic disk, and therefore it may be possible that one can explain the cosmic rays over a larger energy range, not only to the knee, but also beyond the knee, and both particles or both part of the cosmic ray spectra are then related to the supernova. So, thank you for.
What are the observational consequences? The same M82, a very well explored galaxy, right? Is there these shock fronts, the reverse shock and direct shock, are they observable in synchrotron emission, for example?
It could be that they are, yeah. But of course this is a simple picture in the sense that this is a 1D.
Simple doesn't mean that.
Yeah. No, it doesn't mean one. That's true. Yeah. One has to do that. One has to calculate the electron spectra, which I haven't done up to now. If you want to see the synchrotron emission. In this case, I have also the advantage or also the disadvantage that what I do is specifying a diffusion coefficient, which you can get from observations and some other estimates. If you really want to calculate in the synchrotron emission, you have to know what is the structure of the magnetic field, for example, or assume
Maybe can I add something to this? The advantage of this model is, of course, that as we know, there are some galaxies where we can observe the radio spectral index, which has some sort of flat behavior in the halo, and that's of course a problem because you have very high losses of electrons as they propagate out of the field. If they are here then accelerated in a shock, that would be a natural explanation how to actually boost them in energy again against the severe radiated losses.
So in Google, observe the version of galaxies which have spectrum and not near the distance. The acceleration
And if I can add something, which I think is also important in our model here, is that since the shock wave propagates out and it propagates on a density gradient, it is actually very strong. So the Mach numbers are fairly high in this case. These are not just weak Mach number shocks, which is important if you want to reach also high energies in the acceleration. And the second thing is that, I think more importantly, that the source or the injection particles, they are the particles that come from the disk. So it's not so much important that it's the same process, but it's much more important that these are the same particles. So you don't have a problem in measuring the spectrum because you use already the particles from the
Don't you think that there should be additional acceleration of turbulence in that halo? It's impossible that the flow is not turbulent.
Oh yes, yeah.
Then you can have the same acceleration.
Yeah, but it's much more efficient because this is a high Mach number shock of the order of Mach number 50 or so.
Yeah.
But the turbulence will be widespread, volume filling. The shocks will be still, we are not sure how many of them will be available to accelerate a particle.
But they are long-living shocks. That's the other criteria.
Or so to say, almost every supernova exploding then in this superbubble sends a shockwave out there. Of course, the longer the process goes on, the weaker the shocks are, because you have then so much energy that adding a supernova is not relevant, but so to say, maybe 10, 15 shockwaves is general. Every one boosting again the particles by some one order of magnitude or so.
And I ask how far do you get up actually in energy? Because there's this interesting discussion where we actually have to cross over to extragalactic cosmic, so this might be relevant.
Yeah, there is a lot of work still to do on that.
So you cannot give us an
No, what we want to really, I mean, these are the first calculation. What we really want to do is calculate the spectrum of the cosmic rays and then really see how far you can get. In particular, with exploring the parameter space in more detail.
Well, we hope to get to the end. Yeah, but not
Yeah, we hope to get.
We have excellent synchrotron data for M82, the same agent as M82, excellent galaxy.
explore all these effects. Multi-frequency, polarization, evolution. Go to the ball and you
We know a lot on the properties also of the starburst region and the dimensions that we see. Also, if you talk to the observers, they all say that it's a perfect model if you take such a flux tube geometry. Even in their plots, they use this flux tube, which you can really get by this kind of geometry.
Can I ask one thing? Peter Biermann always tells me that he has this model with Friday stars where you have these winds that went off earlier and then there are subsequent shocks where you can accelerate things. What is the difference between your things and this model? Do they complete?
No, he does it basically by increasing the magnetic field. If you increase the magnetic field, you can get to higher energies in the cosmic rays. And he increases the magnetic field in the supernova remnants by exploding the supernova in a higher magnetic field which comes from the wind of the Wolf-Rayet star. This is still confined, so to say, to supernova remnants. Yeah? Here we propose the shock waves traveling in the galactic wind in the halo which do the acceleration of the particles.
I mean, the main problem is, of course, the lightning of the shock, and that can't be so long in the Wolf-Rayet star either, so that's the limitation.
Did you say you can get beyond in the
galaxy? No, but we hope to get up to the beginning.
So the anisotropy won't be a problem in that case.
No, we want to get beyond the need.
No, beyond the need, yes.
But then the engine, but then you will have some problem with anisotropy, which is very, very high, 10 to the 18. You mean coming from a halo of 10 to the 18 to anisotropic?
Well, they can
Coming up and down, but they wouldn't come from the side.
these star-forming regions are supposed to be anywhere in the disk, so you can
But they're accelerating something like the
No, they are
theoretically down, not from the side.
They are accelerated only a few kiloparsecs above the galactic plane.
They can get isotropized.
They diffuse them down.
by the time they come back, they can come from anywhere.
Well, I have one question about this diffusing inwards against the flow, because it's basically similar to solar modulation. So what you get down to the galaxy where you are observing is not a power law by any means, but you would get a bounce, something that near the maximum energy that you can actually get. Because the low energy particles, they have smaller nucleic costs, they only have more trouble coming in. It's similar to, for example, anomalous cosmic rays, which are accelerated at termination, and their spectra are more or less bumps. This would be my expectation on this kind of thing, where you accelerate something which has to be propagated backwards against the flow.
But you accelerate it on several shock waves, not only on one shock. But it does, I mean, if the bump is then at the entry, it's wide. Yeah.